All right, so today I'm gonna give a quick talk about what I learned in my Fluids 1 class. Um, so in the class, we started with a hydrostatic equation, and that led to calculating pressure on submerged surfaces. And we did touch a little bit on like buoyancy, velocity field, and streamlines, but it was more like to tell us that these things exist. We really didn't do problems or examples on these. And then we went into conservation of energy, and that led into Bernoulli's equation. So for hydrostatic equation, since we are looking at a static fluid, there is no shear, stress, or force. So we take out the pressure change in the x and y direction. And after simplifying this z direction equation, we get the hydrostatic equation here. dp over dz equals negative rho g, and we simplify it by integrating, and we end up with the pressure. Our resultant pressure, or the pressure we're trying to find, is equal to our starting pressure minus density of the fluid times gravity, all of that times the depth difference. And then onto an example. This is a homework example I worked on, and we were given the density of salt water here, and we were just told to like search up the density of water and mercury. So this is our assumptions, and we were tasked to find the pressure difference between the point here of water and this point here at salt water. And so we start by calculating the pressure difference, or the pressure of like this 10 centimeters of mercury, and we add that to the pressure being created by the water here, 50 centimeters height or depth of water, and we add them, which will give us this number here, 18.2 kilopascals. And to calculate the salt water, it's much easier because there's nothing being added onto. So we just get 30 centimeters of salt water times the density and gravity to get 3 kilopascals. And so we find that the pressure difference between uh, the circle here for water and the circle here for salt water is 15.2 kilopascals. And we didn't have to worry about air because we were told that the pressure of air is negligible in like this setting. Now onto pressure on submerged surfaces. We were given these two equations. I labeled what uh, each variable is. Like force equals the pressure on the area. And then this is to find where the force is being applied to using the center of the object plus like how, I don't know how to explain IXX. Like yeah, no clue. Um, yeah, we'll just move on to example. Um, so so this problem is about finding the minimum weight of the gate that's needed to like stay closed here. And so we're given that the gate is 3 meters long and 2 meters wide at an incline of 30 degrees. And the fluid is water, and we're assuming that it's static flow, incompressible, and gravity is the only body force. So we start off with a free body diagram of the gate, and we have to calculate where this force is being applied to. So this is where our y sub p equation comes in. And we know that the weight of the gate is being applied at the center of the gate here. And then this is the height to the center, which we'll be using later to calculate, um, where is it? over here to calculate the force. So after we do this free body diagram, we find the moment because that will help us with the weight. So the moment is equal to the force times the location of the force minus the weight cos theta, the angle here, 30 degrees, times length divided by 2 because that is where the weight is being applied to, halfway down this gate. And by isolating W, the weight, we get 2 times the force times the location of the force over the length cos theta. Now we have all of these values, so we just do some quick substituting, and yeah, that's basically it. We just put in numbers into these equations, and then we end up with 68 kilonewtons. Right now, on to conservation of energy. My teacher had a slide with like a big, like long derivation of how to get this to this equation, but he just told us that it wasn't that important and he wasn't gonna spend time going through it. So he just said take this equation and yeah. But to explain it, we have Q dot here, and that is the net rate of heat transfer into the control volume. This W dot shaft is the work that the shaft has done. So like pumps, turbines, and stuff like that. And then here on the right side, this integral here represents the rate of change of energy stored inside the control volume. So it's like how the total energy inside is changing with time. And then this integral here is the energy transport across the control surface. It accounts for energy carried in or out by the flow. And then this end part here, or wait, no, well, to explain what's inside this U is the internal energy. This thing would be the flow work. This is the kinetic energy here, and then this is the potential energy. And then this part at the end is the mass flow rate. So overall, the energy is entering the system as heat and work, and that equals the rate of energy change inside the system plus the energy leaving with the flow. Okay, now moving into the Bernoulli's equation. We get Bernoulli's from the conservation of energy, and so we can remove any terms for heat transfer, shaft work, and unsteady flow, since we're assuming that it's steady, it's frictionless, with no energy loss or gain. That simplifies the equation down to just the pressure, velocity, and elevation, and the mass flow rate, but we're assuming that they're the same, so we can just cancel those out. And then by rearranging, we get this equation here. It's just P1 over density plus V1 squared over 2. It's 2, right? I think so. Plus gravity times the elevation is equal to the second one. Yeah. But onto the example. Wait, before that, another variation of the equation, you could just multiply by density to remove it from the pressure here. So you just get pressure plus density times velocity squared over 2 plus density times gravity times the depth. Okay, now onto the example. In this problem, we're solving for the head loss, HL, and we're assuming it's incompressible and steady. So We have diameters of 0.15 and zero point zero 0.08 with pressure 1 of 480 kilopascals and pressure 2 of 440 kilopascals with a volumetric flow rate of 0.04 meter cubed per second. So in this equation, or in the given, we're not given the depth or the elevation. So we are assuming that they're like equal or negligible difference. So we could just take that out of the equation here. And so first we want to find the velocity. And since we're given v dot, so volumetric flow rate, we can calculate velocity as being uh, volumetric flow rate v dot over a to find velocity. And the equation for area here is pi diameter squared over 4. And since we're given diameter, we solve for both the areas, and then we can solve for velocity 1 and 2 here. And then after that, it's pretty straightforward because we're given everything else. We're given the pressure, we know density, we know gravity, and then we just calculate for velocity. And we were given these alphas. So after just plugging it in, we get head loss of 0.963 meters. Now, before I wrap up, I'm gonna, talk about some theory. So first, when a fluid is at rest, pressure varies with depth due to the weight of the fluid above. That's described by the hydrostatic equation, which we use to calculate pressures on submerged surfaces and find the center of pressure. But when a fluid is moving, we rely on conservation principles like conservation of mass, momentum, and energy. The most important one for us here is energy conservation, which is captured in Bernoulli's equation. It shows that as fluid flows, its pressure energy, kinetic energy, and potential energy trade off of each other, but the total energy along the streamline stays constant. This theoretical foundation is what allows us to model and design systems that handle fluid pressure, flow, and forces. And yeah, thank you for listening in today.